Hello students. Last time we have started this seventh chapter, Raman spectroscopy, and in the first lecture I have explained what is actually Raman effect, and we also seen the classical theory of Raman effect. So where we have studied what is the reason behind the actual modification in the frequency. So, in addition to the incident radiation frequency, there are few additional frequencies observed in the scattered light by the molecules. So, the reason behind that we have studied while studying the classical theory of Raman effect. Now, the same can be also explained by quantum theory. So, quantum mechanical explanation of Raman effect today we shall study now. Okay, so the quantum mechanical explanation of Raman effect, it is based on Kramer-Heisenberg theory of light. Now, what is this theory? According to this theory, when a photon of frequency nu zero, it interacts with molecule of substance, it will jump from any of its initial vibrational or rotational level represented by E dash suffix v dash oblique j dash, where v dash oblique j dash is equal to 0, 1, 2, 3. These actually represent the quantum numbers, either vibrational quantum number or rotational quantum number. To the higher vibrational or rotational energy level, E double dash suffix v double dash oblique j double dash. So in short, you can say that because of the absorption of incident photon of frequency nu zero, the molecule will jump from initial vibrational rotational level represented by E dash suffix v dash oblique j dash to the higher rotational or vibrational level E double dash suffix v double dash j double dash. So this is the process where molecule, the state of molecule will be changed because of the absorption of incident photon of nu zero. Now it may be between the vibrational levels or rotational levels, and you know that the vibrational level excitation or rotational level excitation, that involves absorption of energy by the molecule, and it will undergo a reverse transition. During that reverse transition, whatever the energy it has absorbed, it will be released in the form of photon, and these particular photons, they are actually responsible for the scattered light, whatever the scattered light that we get from the molecule. Now, the higher energy level is unstable. That means when the molecule is excited to higher state or a higher energy level, it is unstable there. It has a very short lifetime of the order of 10 raised to minus 17 seconds. Therefore, the molecule will return to any one of its initial vibrational or rotational level. That means if it has excited from its initial vibrational level to higher vibrational level, so it will come back again from higher vibrational level to lower, or if it has excited from the lower rotational level to higher rotational level, it will come back from higher rotational level to lower rotational level. So both the possibilities, either vibrational or rotational level excitation may take place, and during this reverse transition there will be an emission of photon. Now, depending on the different possibilities, there are three possible ways by which the photon may be emitted. So what are these three possibilities? So these are based on quantum conditions. So let us see what are these conditions. So case first. Now if you assume that the molecule, it may return from the higher excited state to any of its initial state such that frequency of the emitted photon is same as that of the incident photon. So the transition took place in this particular case so that when the molecule returns from higher excited state to the lower state, that means the initial state, it will emit the photon of the same frequency, nu zero. And this is how we are getting the relic line in the scattered light from the molecule. So in terms of levels, you can represent like this. So the higher level you can represent by E double dash suffix V double dash or J double dash minus E dash suffix V dash or J dash, that is equal to H nu 0. So the energy difference will be given out in the form of photon having energy H nu 0, or this equation you can write nu 0 is equal to H, you can take to the left hand side. So this will be dividing the term. So nu 0 is equal to this term divided by H. So that will be the frequency of the emitted photon. So you can represent with the help of energy level diagram how this happens. Suppose these are the levels, either vibrational level or rotational level. Okay, for example, they are vibrational level and they are represented by the vibrational quantum number 0, 1, 2, 3, and here the excited state. So this is the ground state and these are the excited state. So in excited state, suppose they are 0, 1, 2, 3 and so on. Okay, so the ground state energy level, it is represented by this E dash suffix V dash or J dash, depending on whether it is vibrational level or rotational level, and this is the excited state depending on whether it is vibrational level or rotational level. E double dash representing the excited state. Okay, now initially when the photon of certain energy H nu 0, it is incident on this molecule, so it will be going from, suppose, this ground state to excited state. Okay, suppose the initial vibrational quantum number or rotational quantum number is 0, so it will go to the excited state of the number 0 and it will come back again. Okay, and it will give out the photon of the same frequency with the same energy, that is H nu 0. So this is possible for this state also. That means initially, suppose the molecule is in the first vibrational level, this one, then this is second vibrational level, this is third vibrational level, and so on, depending on the vibrational quantum. So from this to this, there will be excitation and it will come back again. See the arrow, both directions are shown here. Okay, so upward transition and lower transition. So therefore both are involved the same energy difference while going upward and coming downward. So therefore the emission of photon here will result into the radiation of the same frequency as that of the incident radiation. Therefore nu 0. So photon of the same frequency nu 0 is given out, and this is true for example 0 to 0, 1 to 1, 2 to 2, 3 to 3 and so on, these types of transition. So this is quantum mechanical picture. So this indicates the presence of Rayleigh line because the same frequency is observed in the scattered light. So as we have seen earlier, this is called as the Rayleigh scattering, or the line is the Rayleigh line in the scattered light. So in the Raman spectra, whatever the original line that you get, that is nothing but the Rayleigh line, and that is due to this reason or this type of transition. So this is the quantum mechanical explanation for the original line that is observed in the Raman spectra. Now let us go to the second case. Okay, so in the second case, we shall assume some different type of emission of photon because of different reason. What is that reason? The molecule in the lower state, that is the, suppose E dash V dash oblique J dash, so that is equal to 0. So the vibrational quantum number or rotational quantum number, suppose it is 0, and suppose it absorbs incident photon and jumps to a virtual level. Okay, suppose it jumps to certain virtual level, either of any of these. For example, let us assume here the 0 level vibrational level in the excited state. Okay, so then it will return back to one of its initial state with the release of photon with lower frequency. So it will come back. Since this excited state is unstable, it will come back. But while coming back, it is possible that it is coming back to one of the initial vibrational level other than its original level, because it has originated from the vibrational level where vibrational quantum number V is equal to 0. But while coming back, it will not go to the same level, rather it will go to either V is equal to 1, V is equal to 2 or V is equal to 3. So what will happen now? See, the excitation energy is this much and the downward transition, this or this or this. See, the transitions which are possible here are 0 in the excited state to 1 in the ground state, 0 in the excited state to 2 in the ground state, and 0 in the excited state to 3 in the ground state. All these transitions, what will happen when this kind of downward transition took place? The photon of lower energy, lower means whatever the energy absorbed here for the excitation, in comparison to that, the lower transition involves less amount of energy. See the energy difference here. The energy difference is higher. Here the energy difference is lower. Again, much lower and very lower. Okay. So photon in this transition given out, they will be definitely having less energy than the incident photon. That means less frequency. So the release of photon with lower frequency, nu s, let us represent it by nu s. The suffix I have used here to represent that it is a Stokes line. Okay. So earlier we have seen that in the scattered light from the molecule, the Raman spectra consists of 3 types of line. The original frequency line just now we have seen in the case first, that is the Rayleigh line, and the one which is having lower frequency than the incident radiation. This is the line, that is the Stokes line. So it has lower frequency than the incident photon energy. So E double dash V double dash oblique J double dash minus this ground state energy, that is equal to H nu S, where nu S represent the Stokes line for these transition. So this actually indicates the Stokes line in the Raman spectra. So this is case second. So quantum mechanically, what is the reason for observing the Stokes line, that is explained here with the help of these energy levels. Okay. Now let us go to the last possibility. Okay, case third. Now, if you assume that the molecule in the higher initial state, for example, the molecule is already in V is equal to 1 state, it is in ground state, but in the higher state, instead of in 0 state, V is equal to 0 state, suppose it is V is equal to 1 state. So, it gains energy from the incident photon. Now, suppose it absorbs the energy from the incident photon, it will be excited to the higher energy level. Okay, that means in the excited state, suppose it goes to V is equal to 1. Now the molecule then returns to any one of its initial state with the release of photon with higher frequency nu A. So it will return, but now it is possible that it will return to this level 0 from excited state V is equal to 1 to ground state V is equal to 0. So what will happen? Now see the energy, this upward transition energy and this downward transition energy. So downward transition energy is higher than the upward transition energy. This energy difference is more as compared to this energy difference. So what will happen? In this case, the photon which is released here or emitted here, that will be with higher frequency, let us call it as nu A, than the incident photon frequency. So incident photon frequency, as I have shown here, so this incident photon frequency, you can see that incident photon frequency, suppose anything that is nu 0, but the photon emitted is having higher frequency nu A, because see this, the transition involves the energy difference that is higher, and this is true for any such lower transition 1 to 0, or suppose initially this has gone to 2, then 2 to 0, or if it has gone to 3, then 3 to 0. So anything. So the initial transition, if the energy is less as compared to downward transition, then definitely you will get a line that is a Stokes line, nu anti-Stokes line. Okay, nu A suffix used here is for anti-Stokes. So all these transitions are true here, which I have just specified: 1 to 0, 2 to 0. You can see here this 1 to 0 or 2 to 0. Initially, suppose it is excited to 2. This indicates the anti-Stokes line in Raman spectra. So in this way, one can give the explanation why we get these 3 types of line in Raman spectra. The Rayleigh line, which is having the same frequency as that of incident photons, the Stokes line, which is having lower frequency than the incident radiation, and anti-Stokes line, which are having the higher frequency than the incident line. So from energy level diagram and the allowed transitions, one can understand how this happens. Okay, so this is very simple way to understand quantum mechanically how the scattering involves these three types of lines. Other than the original frequency line, there are two more types of line, that is Stokes line and anti-Stokes line. So this explanation is possible by quantum theory also. Now, in the second part, we shall study some characteristics of Raman lines. So, these are very important because whenever you are using Raman spectra as a tool, spectroscopic tool to study various parameters of the matter, then these characteristics of Raman lines, they are very important. So, one must understand what are these characteristics of Raman lines in the Raman spectra. So spectroscopy, you know that use of the radiations to understand the properties of the matter. Okay, so the radiations are incident upon the matter, and the interaction involved between the radiation and the matter is studied. That is nothing but a spectroscopy. So in spectroscopy, Raman spectra is also very important, where we are studying the interaction of monochromatic light with the matter, and the scattered light, the shift, Raman shift is studied, and from that very important information can be retrieved regarding the uh, molecules, okay, or the matter. And some of the application later on we are also going to study. But before that, we must know different characteristics. So first characteristics that we are going to study here is intensity of Raman lines. Okay, so intensity of Raman lines, it varies as nu 0 minus nu vibration bracket raised to 4. So what is nu 0? It is the incident frequency, and nu vibration, the whatever the molecule involved here, the vibrational frequency of the molecule, that is nu vibration. So if you take the difference, fourth power of this difference, that will decide the intensity of Raman line. Except, there is one exception, near the vicinity or the vicinity of Raman resonance scattering. So whatever the resonance frequency of that molecule, that very near to that, there will be an exception. Okay, so intensity depends upon frequency of radiation. So what conclusion we can draw here is intensity of Raman line, that depends upon frequency of radiation. So whatever the incident frequency, that is important for us. So that will decide what will be the intensity of Raman lines. Then if you compare the intensity of anti-Stokes line and Stokes line, so it is observed that generally anti-Stokes lines are fainter than Stokes line. So that means here Stokes line having higher intensity and anti-Stokes line are having lower intensity. Then one more thing, that it is observed that intensity of anti-Stokes line increases with temperature. So as you increase the temperature, it is observed that the intensity of anti-Stokes line also the intensity of anti-Stokes line also increases. Okay. Now second characteristics we shall study here is width and shape of Raman line. So usually Raman lines are narrow for gases, liquids and crystals. If you observe the Raman spectra, you will get very narrow lines for gases, liquids and crystals. But if you consider a particular state of matter, that is amorphous substances, okay, so you know that amorphous substances have a very microcrystalline structure, they are randomly oriented, there is no regular structure, okay, so such a matter, amorphous substance, for amorphous substance, the Raman lines are very broad and they are also diffuse. They are not sharp, they are diffuse. Then the width of Raman line increases with increasing temperature. So if you increase the sample temperature, definitely you will find that the width of Raman lines, that will increase. Then the shape of Raman line is independent of the incident radiation. So whatever the frequency of the incident radiation, that will not going to change the shape of the Raman line. Rather, it is not the parameter which affect the shape of the Raman line. Then third and very important characteristics is the frequency shift. Frequency shift means what? You know that the normally in Raman spectra you will get in addition to original frequency of incident radiation, you will get two more lines having slightly different frequency than the original frequency, and they are symmetrically placed, one to the left and one to the right. Left and right means having slightly lower frequency and having slightly higher frequency than the relic line. So this how much it is shifted from the original line, or what is the difference between these two lines from the central line. So that let us call as delta nu. It is called as the Raman shift. Okay. So this Raman shift or frequency shift of these lines from Rayleigh line varies from 4000 to few wave number. Okay. So in spectroscopy, you know that the shift is not measured in frequency, rather it is measured in 1 upon lambda, that is nothing but wave number. So that shift is of the order of 4000 up to few wave numbers. Okay, that means few wave numbers means less than 100 also. Okay, and it is independent of frequency of incident radiation. This Raman shift or frequency shift, it is independent of the frequency of incident radiation. So this very important characteristic. And fourth characteristics, that is related to polarization. Now polarization is very important term. Okay, so in spectra, Raman spectra especially, so Raman lines are partially polarized. So whatever the state of polarization of incident radiation, irrespective of that, there will be partial polarization of Raman lines be observed. So this is very important thing about the polarization of Raman lines. Then it is observed that the polarization depend on structure of the molecule as well as symmetry of vibrational motion. So what is the structure of molecule and what is the symmetry of vibrational motion, that will decide the polarization. Okay. Then the scattered radiation may be polarized in a plane parallel and perpendicular to the plane of polarization. So there are two directions in which they may be polarized. The scattered radiation may be polarized either plane parallel or perpendicular to the plane of polarization. Okay. So let us assume that if suppose I parallel and I perpendicular are the intensities of scattered radiation polarized in parallel and perpendicular planes respectively, then if you take the ratio of these two, I parallel to I perpendicular, it is called as degree of depolarization. This is very important parameter regarding molecules, which is known as degree of depolarization, and it is denoted by rho. So rho is equal to I parallel divided by I perpendicular. What is I parallel? It is intensity of scattered radiation polarized in parallel plane, and I perpendicular, it is the intensity of scattered radiation polarized in perpendicular plane. So if you take the ratio, that is called as a degree of depolarization. So what is the significance of degree of depolarization? So this is an important parameter that plays important role in determining the symmetry of vibrational modes. So actually in chemistry you might have studied the symmetry, vibrational symmetry or vibrational modes, symmetry of vibrational modes. So linear vibration or angular vibration, in plane vibration or out of plane vibration. So there can be a different symmetry, and the degree of depolarization will be important parameter in determining this symmetry of polarization modes. For example, some of the figures are mentioned here, standard figures that can be used to predict this symmetry of vibrational modes. For example, if rho is less than 3 by 4, then you can confirm that the modes are totally symmetric. The vibrational modes of a molecule are totally symmetric if rho is less than 3 by 4. And if rho is equal to 3 by 4, then you can say that the modes are not totally symmetric. The vibrational modes are not totally symmetric for the molecule if rho is less equal to 3 by 4. And if rho is less than 6 by 7, then vibrations are asymmetric and capable of polarization of radiation. So in this case, polarization of radiation will take place. And the vibrations are totally, you can say they are asymmetric. And if rho is greater than 6 by 7, depolarization of radiation occurs. So if it is already polarized, then it will be depolarized. Polarization, the opposite process, it is called as depolarization. So this is the significance of the degree of depolarization parameter rho. So that is very important for determining the symmetry of vibrational modes of the molecules. So in this way, today we have studied some of the important characteristics of Raman line, and we also discussed the quantum theory of Raman effect. In the next video, I shall explain the experimental setup for Raman effect, and finally we are also going to study some applications of Raman effect.